Segment 18, Atomic Structure. An atom consists of a massive nucleus containing a proton in the case of hydrogen, or a proton and neutrons in the case of heavier elements, orbited by one or more electrons. A hydrogen atom has one proton at its center with one electron orbiting around the proton. The proton has a positive electrical charge, and the nuclei of other atoms have positive electrical charge as well. The electron has a negative charge and is about 2,000 times less massive than the proton. Since opposite charges attract with a force that goes as 1 over r squared, like the law for gravity, we expect that the electron orbit would obey laws like Kepler's laws. Other atoms have additional protons in their nuclei and additional electrons orbiting around their nuclei as well, making the case a little more complex. They also have neutrons, which are electrically neutral particles with masses similar to the proton masses in their nucleus, and this has a small but measurable effect on the structure of the atom. Now, it's complicated by the nature of these very small particles. We normally like to think of electrons as particles, but like photons, they have both wave and particle properties. The height of the wave in the case of the electron describes the probability of finding the electron in different places. The wavelength of the probability wave is related to the electron speed by the equation lambda is equal to h, Planck's constant, divided by m times v, where m is the mass of the electron. In an atom, an electron must orbit at a distance from the nucleus so that an integral number of probability waves fits around its orbit. This causes only certain electron speeds or energies to be allowed. So unlike in the case of a solar system where planets can orbit anywhere, in the case of an atom, electrons can only orbit at certain distances. This leads us to a model, for example, for hydrogen, which we call the Bohr atom, which shows these fixed distances where the orbits can be, and they correspond to different energies. So on the left you see a diagram showing the different energy levels, the first, second, third, and so on, and the transitions between them. And on the right you see an energy diagram where energy is plotted on the y-axis, and you see that the transitions from the ground state, the one state, the fundamental level, to higher states are labeled L alpha, L beta for Lyman alpha, Lyman beta, and so on. And the ones from the second state, the first excited level, are labeled H. These are the so-called Balmer lines, H alpha, H beta, and so on. These are the transitions of hydrogen. Now, when you think about this in a more realistic way, the location of the electron can be thought of as a probability cloud around the nucleus. We can't pin down the exact location of this particle, but we can characterize it by its average distance and by the well-determined energy of the state. So you can think of it as a probability cloud around the proton. Different atoms have their energy states with different energies. So hydrogen has these very characteristic states, first, second, third, and so on. Helium does too, but they have different energies than the hydrogen states. And more complex atoms, heavier atoms, have even different sets of energy states. So each atom has a unique set of energy states. And if you remove one electron from an atom that would normally have more than one, for example, taking one away from helium, so instead of two it only has one, then the energy states are different yet again. These ions, the ionized atoms, have even different energy states. Why does this matter? Because photons each have a characteristic wavelength, and we talked about this before. The energy of a photon is inversely related to its wavelength. The energy is hc over lambda, where h is the constant, Planck's constant. What this means is that photons that correspond to the energy difference between two states of an atom can interact with it. So here, for example, you have a diagram of some atom, and photons are coming along. If the photon exactly matches the difference in energy between two states, it can be absorbed by the atom, and the electron in the atom can jump from one state to another. If the photon does not match the energy difference between the two states, it just passes right through. So in this case, you have these 3 photons coming in, and they match the energy difference between the first state and the second, or the first state and the third, or the first state and the fourth, and they can cause a transition of the electron from that first state to one of the higher states. A big jump for an electron requires a higher energy photon, or a short wavelength of light. So these larger jumps correspond to shorter wavelengths, to photons with higher energy. So here is a full-up diagram of the energy levels for the hydrogen atom, and you see at the bottom the transitions to the ground state of hydrogen, and these transitions are all in the ultraviolet. This is the Lyman series of hydrogen. We don't normally see these lines. The lines we see are the Balmer series lines, which come out at visible wavelengths from H alpha, which is the jump from the third state to the second state, which is in the red part of the spectrum, up through lines like H gamma and H delta, which are coming out in the blue part of the spectrum. Then the jumps to the third state are all in this is the Paschen series, are all in the infrared. We can't see these. These come out at longer wavelengths than our eye can see.